says the only wavelengths of light that it shows are the ones in the visible range. So we can actually see them if they fall in this range. Now the visible range is very small. So there's some that are in the IR range and the UV range. Says propose a hydrogen electron transition that involves light with a wavelength in the UV range. So the UV range is from 10 to 400 nanometers. So we talking big wavelength or small wavelength?
Small.
So we want a small wavelength. So which of these diagrams? A, right? A's got the smallest wavelength. And that's the big transition, right? It goes down the most. See how it's showing with the size of the arrow?
Yeah.
It's showing the biggest jump. So in order to have a smaller wavelength than that, you must have an even bigger jump. So what could be bigger than 10 to 2? I mean 6 to 2.
Bigger than that?
Bigger, a bigger jump than going from level 6 to level 2.
7 to 2, 8 to 2.
7 to 2, 8 to 2. If you're going based on this diagram, it would have to be
6 to 2.
6 to 1.
6 to
Yes,
1.
yeah.
Oh, that's what the question was asking.
Right?
Okay.
Yeah, that's what it's showing. Each gap here is quantized amount. It's a finite amount of energy. So the further you jump, the more energy that you've just released. So B says you get a transmission in the infrared region when you've got a wavelength that's somewhere between 1,000 and 106 nanometers. So 1,000 nanometers. That's a huge wavelength. So look at your biggest wavelength, D, and that's going the shortest distance, right? That's the smallest arrow, so it's the smallest amount of energy. So can you see, based on the widths of those rings, which one could possibly be a smaller transition? 6 to 5, yeah. Right? You've just got to go really small. It's a really small amount of energy.
That makes sense. Yeah.
So here we have some line spectra. So they're not colored, but they do show you where the wavelengths are that they where they emit. So lithium has 4 bands. Hydrogen has 4 bands. They do not line up with lithium. Helium has got what, 5 bands?
What does he say? Because one is like connected down.
Oh, no. It's not connected down. 3, yeah, no, it's got 6, yeah, sorry. And then sodium has 2, 2. So, what can you tell me about the spectra for the elements based on those 4? I'm looking for the words like elements, same, elements, different.
Lithium and helium have the same number of.
So lithium and hydrogen have the same number.
Yeah, that's what I meant. H as like hydrogen. Sorry.
But are they in the same position?
No.
So what can you say about all 4 of these elements? What can you say about them and their spectra?
None of them are the same as any of them.
None of them are the same. They're all unique. Yeah.
Oh, that's like a fingerprint. Like
Yeah, they're all unique. So when they look into space And they're using their giant telescopes, and they measure the amount of light and the color of light. That's how they can say, oh, on that gas planet, we know it's this, or the atmosphere around this planet contains this gas. It's not because they've gone up there and sampled it. It's because they can tell based on the light.
I always wonder this kind of stuff, like how do they exactly know
Yeah.
how much Jupiter weighs or stuff like that? How?
If they know what it's made of, or they think they know what it's made of, yeah. Okay, so we've got this unknown. If the element is in the unknown, it will have lines at the same spots, right? Because it's unique. So look at lithium. Is there a band in lithium that is not in the unknown?
Yeah, there's 4 of them.
One of them is pretty obvious, right? This one definitely is not in the unknown. So we do not, our unknown does not contain lithium. It has to have all 4 lines in the same spot. Hydrogen has 4 lines. Does it have 4 lines in the same spot?
Yes.
All right. Looks like we've got hydrogen. Helium.
Yep.
Yep.
Sodium, no.
And then sodium, no, because it definitely does not have that one. There you go. The unknown contains hydrogen and helium. Bless you.